Okay, welcome again, everyone. Good morning, good afternoon, good evening, and welcome to Photonics for Quantum 2. We just had an excellent sponsor talk, and now we're going to have the main talk, which is going to be given by Carmen Almudéver of TU Delft. Carmen, if you could go ahead and join and share your screen, and I'll stop my video. Welcome, and thanks for agreeing to give this talk.
Thanks to you. Yeah, let me share my screen. You can see my screen now, right?
Yes, it looks good. Thank you.
Okay, thank you. So first, I would like to thank the organizers and especially to Sonia Larcon for having invited me to give this talk today and giving me the opportunity to share the work that we are doing on quantum computer architectures at TU Delft. Although I'm not an expert in photonics, I'm very happy to be here today in front of this audience because, as I will explain at the end of the lecture, I think photonics will be key for developing like scalable quantum systems. That is one of the main challenges that we have nowadays. So say that before going, let's say, to the more technical part of this talk, let me introduce you a bit more. Let me introduce a bit more at the place where I work. So let me see, it's not working. Yeah. So as I say, I work at the Delft University of Technology in the Netherlands. More specifically, I'm an assistant professor at the Quantum and Computer Engineering Department of the Faculty of Electronics Engineering, Mathematics and Computer Science, but I'm also part of QTech. As you may know, QTech is a research institute on quantum computing and quantum internet that was founded around 7 years ago as a collaboration between our university, TU Delft, and TNO, that is an engineering company in the Netherlands. And it's also a collaboration between two faculties within TU Delft, so the Faculty of Physics and the Faculty of Engineering. So as you may also know, in QTech, we work on different quantum technologies, and therefore we are organized in different roadmaps with different goals. So these roadmaps, and you can see here in these pictures, are the topological quantum computing, which goal is to develop and build and demonstrate the first topologically protect quantum bit, and based on Majorana's technology, or based on Majorana's. Then we have QUINC, that stands for Quantum Internet and Network Computing, that the goal is to build an optically connected network of many small quantum processors based on MB centers, but also to build quantum internet. And then the third roadmap, that is the one that I belong to, is the fault-tolerant quantum computing roadmap, that our goal is to build a full stack scalable quantum computing system. This full stack includes, as I will discuss during this presentation, from qubits to the control electronics up to the upper layer of this full stack, that are the software layers. And we also, our goal is also to achieve fault tolerance based on quantum error correction. So I have to say that the work that we develop within this fault tolerant quantum computer roadmap, we do it in very close collaboration with Intel, that we started a collaboration in 2015. So now this, I don't know, sorry for this. I don't know why this is not working. Let me just switch off the laser point, maybe because of that. Yeah, okay, better now. So let me start like just saying what a quantum computer is and or is not. So as you know, a quantum computer is not going to be a replacement for a classical computers. So quantum computers will be good at solving some problems that are intractable, even for the most powerful supercomputers that we have nowadays. Some examples are, for instance, like quantum simulation, that in which we can simulate chemical reactions and develop, for instance, new drugs, or other examples are optimization problems that we have an impact in several industries like logistics. Like a quantum computer is also a very good example of what we call an in-memory computing device or memory computing system, in which memory and processing or computing happens in the same place. As you may know, nowadays, classical computers, they follow is what we call a Riemann architecture, in which you have let's say, an area for processing and another area for memory, and data has to be sent back and forth, and is one of the main bottlenecks of the current computers. And the third point that I would like to make is like we always say that we are building a quantum computer, but actually what we are building is a quantum accelerator or coprocessor. So nowadays, what we have in classical computing and heterogeneous multi-core systems, in which you have the main CPU or the host CPU, and then you have like several coprocessors in which a specific task are accelerated or executed. For example, some of these coprocessors can be an FPGA or GPU, TPU, and why not at some point to have a quantum accelerator. And this mobile computation is the one that for sure, or I will say it for sure, we will follow in the next years. In the next year, we'll have like smaller scale and intermediate scale devices, but maybe also in the future, and most of the quantum applications are hybrid applications in which you have still a classical part that will be executed in the host CPU, and a quantum part that will be sent to your quantum accelerator. So what is quantum computing now? So as you know, so the idea of building a quantum computer is not something new. It's something that was already proposed by Richard Feynman back in the 80s, in which in one of his talks, he proposed to build a quantum computer to simulate quantum mechanics. Since then, it has been a big progress on quantum computing, from the development of the first algorithms, like the Shor's algorithm in the early 90s, to the development of the first quantum computer based on quantum annealing by D-Wave. And nowadays, we are just basically exploring different quantum technologies in order to build qubits. Those technologies are trapped ions, quantum dots, Majoranas, photonics, or superconducting circuits. Now we are in this phase in which big companies, IT companies like Google, Rigetti, IBM, Intel, Alibaba, are in this race in which we are trying to integrate more and more qubits in a single processor. And of course, one of the last breakthroughs that we have last year is the achievement, or not, I will put here a question mark, but it's still a very nice experiment of quantum supremacy by the Google experiment. Right now, we are in the NISQ era. NISQ is something that was proposed by Preskill in his paper, and it stands for Noise Intermediate Scale Quantum Devices, in which we have like relatively small quantum processors integrating like tens of qubits, and that they are affected by noise. And of course, this noise will place serious limitations on what this quantum device can achieve in the next years. So, as I just mentioned, right now we are exploring different technologies, and for instance, superconducting qubits and trapped ions are one of the most promising ones, because they have been able to integrate more qubits in a single chip or core. And one of the main issues for all these technologies, as you know, are the coherence time, like can vary from microseconds up to seconds for silicon spin qubits, and also the high gate error rates, or relatively high error rates that we have. But something that I would like to emphasize here too, another issue that we have in current devices, and I think we will also have in the future, is the connectivity or limited connectivity among all these qubits. For example, in trapped ions, we can have all-to-all connections. That means that any pair of qubits can interact, but in others like superconducting qubits or silicon-based qubits, we only have near-circuit interactions. And that will pose, as I will explain in the next slide, some challenges when you want to run a quantum algorithm on this kind of devices. Also, in terms of applications, I took this graph from this report that was published by Boston Group Consultancy. And I'll keep it much because you can show the different kind of applications based on the robustness, or how robust they are against errors, and the theoretical speed up that we can achieve with these applications. So one of the most famous applications that can give us up to exponential speed up are the Shor's algorithm or the HHL algorithm for linear solvers. But we know that in order to be able to run this kind of applications, we still have to wait more than a couple of years, as we will need like very large number of qubits and a computer that is fault tolerant and resilient resistance to errors. But in the short term, and that's what we are doing nowadays, there are other very interesting applications that are quite robust against errors. And they use these hybrid approaches in which a classical, let's say, classical solver is combined with a quantum solver. Some examples are the BQE algorithms or the QA or OA algorithms. Okay, so far, I've been talking where quantum technology is and where we are in terms of quantum algorithms. But what if we want to run these quantum algorithms in a specific quantum device? So in order, let's say, to bridge the gap between quantum applications and quantum chips, what we need to build is what we call an architecture. Or in other words, several layers, again, that connect for being able to execute this algorithm on a specific quantum chip. These are the layers that are shown here in this picture. So you have at the top layer your quantum algorithm. This quantum algorithm has to be expressed in a high-level programming language. This high-level programming language, through the compiler, is then translated in a series of instructions or expressed in low-level language that belong to the quantum instruction set architecture, and through the microarchitecture, they are translated in a series of pulses that operate on your quantum chip and execute the algorithm. And of course, here you can see in the third dimension that if we want to build a scalable fault-tolerant quantum computer, we will need to use some kind of error correction or even error mitigation for having a high probability of success. Now, let me give you an example of this what we call full stack or quantum computer architecture. So here you can just express, as I say, your circuit using a high-level programming language. In this case, is Python. Through the compiler, this high-level language can be represented as a circuit and translated in a series of low-level instructions, usually based on QASM. QASM stands for Quantum Assembly Language, and it has this form. It's just the expression of each of the gates in your circuit. And finally, these instructions are translated in a series of pulses that operate in your qubit. Because as you may know, for instance, in order to apply a Hadamard gate in a superconducting qubit, what you have to do is to apply a microwave signal with a specific frequency, amplitude, and envelope. Nowadays, there are different quantum softwares that are being, already developed for going from this high-level expression of your algorithm down to the chip. That, for example, the OpenQL that we develop here at Delft, but you also have some other quantum software like the Quantum Development Kit from Microsoft, or Qiskit from IBM, or Forest from Rigetti. So this full stack that I just mentioned is exactly what we use in our labs, in in Delft. This is just the setup for superconducting qubits. So here is a superconducting processor with two star-mons. And as you may know, so the superconducting processor is in the coolest stage of the cryostat that is inside this fridge. And this fridge is in the ground floor of QTech. And here you see all these cables that go to the first floor, in which we have all the electronic devices in order to control and to operate on the superconducting processor. Here you have AWGs, QWGs, and other devices indeed for generating the signals. And I would like to emphasize this small box here. That's what we call the control box, and implements the microarchitecture. And when it does, what it does is just to orchestrate the other devices in order to send signals at proper time and with a specific waveform. This full stack is also integrated in Quantum Inspire. Quantum Inspire is the first platform in the cloud that has in Europe, that has been developed also at QTech, and in which you can operate on different backends. So I think it was launched a couple of years ago, and before we only had, and at that time we only had the QX simulator, in which you could simulate the qubits. But recently, last April, we added two more backends. One is a processor based on spin qubits, and we have two spin qubits, and the other is the Starmon 5 that is composed of five superconducting qubits. It's similar to the quantum experience in IBM. So now, what are the challenges when we want to build this full stack system, or like the full stack computing system? So the first, indeed, it's about the quantum devices. As you know, there are several challenges there that we need to overcome. The first one is to enhance the coherence time of the qubits, the operation fidelity, and also the scalability to build larger systems. The other is related to the control electronics. So right now, as I showed in the previous slide, in order to control the qubits, you have the chip in the cryostat, in the fridge, in the coldest part of the cryostat, and the control electronics are placed at room temperature. That means that there are plenty of cables going to raise room temperature down to 20 millikelvins. And of course, this approach is not scalable. So some techniques that we can use for reducing, the number of wires is to use, for instance, multiplexing, but also to move electronics down to the quantum chip, operating at cryo temperatures. Or another technique that there are really some papers about that is to build what they call hot qubits, that are to place some of the qubits at 4 Kelvin. And then the last challenge, and that's the one that I will focus in the next slide, it's about the development of the software and the hardware in order to control this system. As I just mentioned before, in order to bridge the gap between the application and the quantum chip, we need to develop programming languages, compilers, instruction set architecture, and related microarchitecture, and develop this hybrid classical quantum paradigm, or this heterogeneous system, as I just mentioned before. Now I will focus on one of the specific problems that arises when you compile quantum circuits and when you want to execute them on these devices. So one of the main challenges when you want to run a quantum circuit or a quantum algorithm on a specific device is that you have to somehow transform the circuit in order to satisfy the constraints that the quantum processors might have. Let me illustrate this with an example. So imagine that you have this circuit here on the left that is composed of 7 qubits and different single qubit gates and 2 qubit gates. And this is just the representation in terms of quantum instruction. So now let's assume that we want to run this circuit on this processor in which each of the dots represents a qubit and each of the edges possible interactions between those qubits. So the first that we can do is just to schedule the operations in order to leverage parallelism. In other words, these instructions or these operations can be just performed one after the other, but indeed, as we are limited by the coherence time, it's better indeed if we just perform some of these operations in parallel. So the second thing is, okay, I have here my qubits in my circuit that are usually called also logical qubits or virtual qubits, where they are placed in my physical device. In principle, I can just do a one-to-one mapping like Q0 in the first position, Q1 in the second one, and so on. But as there will be some qubits that will need to interact afterwards when they have to perform this 2-qubit gate, it might be more interesting to place those qubits in a way that those qubits that need to interact a lot between them, they are really placed in adjacent positions. Yeah. If we do so, if we do like a kind of optimal initial placement of the qubits, we can see in this circuit that the first CNOTs in the circuits can be executed without any problem because those qubits are next to each other. For instance, CNOT between Q3 and Q4 can be performed as they are next to each other. The same for Q3, Q5, they are next to each other, and so on. But here, for instance, if we go through the 4th layer, let's say of my circuit or my algorithm, there is a CNOT between 0 and 5 and 2 and 3. And if we look where the qubits are placed here, 0 and 5, they are not connected, so therefore they cannot interact. The same for 2 and 3. So what we do in order to do those qubits adjacent, what we do is to insert some swap operations. That's for superconducting technology, for instance, in which we just exchange the states of some qubits in order to make them adjacent and therefore that they can interact. So this process, or let's say of moving qubits next to each other when they need to perform, in this case, a 2-qubit gate, a CNOT gate, is called the routing of qubits. As you can see here, the routing means just looking for a path to put the qubits next to each other and to insert the respective movement operations, in this case, swap operations. And you can see also in this example, this increases the number of operations in your circuit. This increases, of course, the circuit depth, and therefore decreases the probability of success of your algorithm. So this, let's say, this step in the compilation of your quantum circuit is key in order to still have a high chance of running your algorithm successfully in your device. Now, What are other constraints that we can encounter in our quantum devices? So in the previous example, I just talked about the connectivity constraint, right? That is this nearest neighbor interaction, but there are other hardware constraints. The other, as you may know, is the elementary gate set. So in a chip, you cannot perform any kind of operations, but just a reduced set of operations in which an algorithm can be expressed. This is called elementary or primitive gate set, and usually includes single qubit rotations as well as 2-qubit gate, like for example, the C phase. The other limitation that I just mentioned before is the limited connectivity between qubits and the topology of your chip, that sometimes is just limited to nearest neighbor interaction, like is, for example, the Surface 17 that was developed by QTech and Intel and other IBM chips. And the third constraint that is not really like mentioned in most of the papers in mapping is the classical control constraints. This comes from the fact that sometimes whenever you want to build a scalable quantum system, control electronics are shared among qubits and they're shared in terms of frequencies. That means that poses some limitations in what operations can be performed in parallel in the real chip. So let me elaborate a bit more about this compilation or mapping problem. So the mapping problem, it's an NP-complete constraint optimization problem. And one of the main approaches that the community working on this topic are following is just to use heuristics in order to, let's say, to rebuild the circuit to respect the constraints. This requires, let's say, an initial placement and then to add some extra operations that I just showed in the previous example. This problem can be solved using different solvers that, for example, STM solvers, or greedy randomized search, or genetic algorithms. There are also other approaches that are inspired. They use AI, like for example, they use temporal planners, but editors combined with constraint programming, or also reinforcement learning for qubit routing or for movement of qubits. So as I mentioned before, so the mapping mostly affects the reliability of your algorithm or the probability of success. Therefore, one of the cost function or the main cost function that is used when doing the mapping is the number of ways of gates. You want to minimize the overhead in terms of gates or the number of sub-gates that you add. You want to minimize, of course, the circuit depth because, again, you are limited by the coherence time. But at the end, what you want to achieve is a high success rate of the algorithm, right? So that's why there are some researchers that they started proposing like a cost function or like a factor to take into consideration when you do the mapping is the reliability between the qubits in your circuit and the links between them. But recently, last year, for instance, was this is a work that was published or was done by a Martinosis group in University of Chicago, in which they take different quantum devices from IBM, Rigetti, and also Trap Ion from UNDTI. And what they do is to try to map several algorithms in these kind of devices and using as a metric the reliability, again, of the links of the qubits. So for example, in the case of IBM, they, let's say they observe the error rate between the different links of the quantum chip for 26 days, and they build a reliability matrix in a way that whenever you want to place an algorithm, you take again the more reliable qubits and the highest like operation, fidelity operation among them, in this case, the CNOT. And by doing that, they calculated, let's say, the success rate or probability of success of the different algorithms on different devices. And of course, you can see here that the one on the one on ion traps that has all 12 connections, have the highest probability of success, as they don't need again to move qubits around to do any kind of routing. Yeah. So in QDEL, we also develop our own, let's say, mapper that is called QMap. QMap, what it takes as an input is the quantum algorithms that can be written in OpenQL. OpenQL, again, is a high-level programming language. It can be Python or C++. And it consists of different steps, the ones that I just mentioned before, that is initial replacement of the mapping, let's say, from the qubits in your circuit to the qubits in your chip. It has a router that is to calculate the different paths to put qubits next to each other and insert the corresponding operations, and the scheduler that is just to parallelize the operations. So the good thing about this mapper, and also other mappers have that, is like we express all the constraints of your chip in what we call a configuration file. In this configuration file, we include information like, for example, what is the elementary gate set of your chip, what is the duration of its gate, what is the method for decomposition, what is the chip topology, and other classical constraints. And by doing so, we have a flexible, let's say, mapper in which you can map any quantum algorithm to any kind, for example, of device like the Surface 17, again, developed with QTech and Intel, or the IBM Q Tokyo. So just by changing, let's say, the parameters here, you are capable of running different algorithms on different devices. But we also try to map, let's say, to use this mapper to map your quantum algorithm in a completely different device. This is just a proposal or a crossbar based on silicon spin qubits. And we realized that here, I mean, you really need to change the way in which or the strategies that you use for mapping your algorithms, because, for instance, here, instead of using swapping, you use shuttling. And that's fundamentally different. And that means that, again, the strategy for the routing and the mapping should be changed. So it's very difficult, let's say, to come up with a solution that is universal and can be applied to any kind of technology or device. So just to summarize this couple of slides, so now what we aim is like to develop optimal mapping strategies, and to do so, that depend on both on the characteristics of the algorithm, and of course you have to take into account the quantum processor constraint. There are several approaches that you can have, like a technology specific compiler that applies only for this technology, or like more general purpose compiler that can be applied to any technology because it's a kind of black box, like, for example, the strategies that they follow when they use AI. Then in terms of metrics and cost functions, as I mentioned, the most popular ones are the number of swaps or the circuit depth or the reliability, but this needs further research because it might be also a combination of some of them depending on the technology that you are targeting. And most important so far, we have been following what we call a bottom-up approach. In other words, we are just developing mapping solutions, so compiling strategies for a specific chip and for a specific technology. But what I will say is, like, now the community, let's say, is changing, working on this topic, or the computer engineering committee, we are changing towards what we call a top-down approach, in which you have to take into account, let's say, the application characteristics in order to develop your mapping techniques. So in Delft, what we started doing is what we call a full stack vertical co-design framework. With this framework, based on design space exploration methodologies, what will allow is to do a top-bottom and bottom-up optimized design. So again, by using this framework, and would be very, very critical, especially for niche devices, because as I say, you have to, let's say, to leverage the capabilities of your quantum device. So using this framework, we could optimize for a specific technology and architecture, or in other words, to derive optimal designs of your full stack quantum system. We could also provide hardware design guidelines, or in other words, for instance, for this kind of application, this configuration of the chip works better than this other configuration of the chip. And of course, that will allow us to perform what we say scalability analysis, or just by making some assumptions on the future devices, we can see in what regimes or what, for example, what will be the error rates or the coherence time that we will need in order to have these scalable systems. And finally, and most important, by using this a full stack vertical co-design framework, we could benchmark quantum systems, not only for the full stack, but also against different quantum technologies. So it's in those lines that in order to do so, in order to do this benchmarking of the quantum system, what we are missing nowadays is the definition of a complete and representative set of quantum benchmark and also overall performance metrics. So in these lines, there was a publish that was recently a paper, that was recently published by Cambridge Quantum Computing, together with people of IBM and Glasgow University, in which what they do is they propose three kinds of benchmarks in order to evaluate the performance of your computer. So they classify them in shallow circuits, square circuits. Square circuits, for instance, are the ones that are used for IBM, proposed by IBM to calculate the quantum volume. That is a kind of the first attempt to define a performance metric. And the third class is the deep circuits. They also propose different figure of merits that are all related, let's say, with the fidelity of your or reliability of your algorithm. And for them, they use the heavy output generation, the cross entropy, and the L1 known distance. Doesn't matter what exactly they are, but in somehow what they do is they compare the ideal output probabilities with the distribution, with the output distribution that you will get when you run your application on a real device and therefore under noise. And it's exactly, for example, what they show here, that is the heavy output probability when your application or your application is run, let's say, on a real device or in a simulator under noise. And of course, if you see here the ideal one, so without noise, so this output probability is 0.8, 0.9, and it goes much lower whenever you run it in a quantum device under noise, and also when you start considering, let's say, the constraints of your device. So that brings me to the last part of my presentation. So far I've been focusing, let's say, on niche devices and therefore in single core architectures. But in order to build, let's say, more scalable systems, people started proposing, like Lieven van der Steppen and QTech, started proposing distributed or modular architectures, in which instead of having just a single core, a single processor, you have several processors, in this case, kind of array of spin qubits, and then some coherent interconnection between them. This coherent interconnection can be made of different technologies, but of course, one of the technologies that could be used to build these links is photonics quantum. And this proposal also allows, for instance, to place classical electronics, so it gives you some space to place the classical electronics next to your quantum chip. So, but what they neglect in this proposal is to add the communication perspective. Or in other words, once you have a distributed system, you need some kind of control plane in order to orchestrate the different communication and computation between the cores. And this is exactly what I'm working on together with Professor Eduard Alarcón from UPC in Barcelona, and is the idea of having a double, what we call a double full stack. So far in the previous slide, I showed, let's say, the full stack for communication, but once we go to this, again, distributed system in which many processors are integrated and connected, we need also a communication stack. This is inspired, of course, in classical systems, like in network on chips, again, in which you have your data plane and you have your control plane, that the control plane, what it does is just to orchestrate the communication between the different cores. And just to make the link with the previous topic that I explained, that is the mapping of quantum circuits, as you can see here, now we will have the problem of mapping not only the circuits to a single core, but also to distribute them in different cores in a way, or quantum cores, in a way that the communication overhead is reduced or is limited. So with this, I would like to finish my presentation, not before saying thanks to the members of my group, my colleagues at QTech, and also my collaborators at Intel. So yeah, thank you very much for your attention, and I will be happy to answer any question that you might have.
Okay, Carmen, thanks very much. I'm clapping on behalf of all the participants who are muted, and thank you for a fantastic talk. Let's take a look at the chat window, and I'll leave it to you, if you'd like, to go ahead and read any questions you see in the chat, and we have plenty of time.
Okay. So there is a fair question that are, what are the photonics models that are used for quantum computing? I don't know if I really got this question. You mean like in terms of communication or between cores in the last slide? I don't know if you could please elaborate on this question. So as I just, I'm not an expert, as I say, on photonics. So what I was interested in, what I'm interested is like what I just mentioned at the end of my talk, that is this photonic lens, this possibility of having like a coherent interconnections between different cores, and for that just to use photonic links for this communication. Any other question? You can further elaborate on this question?
Well, actually, I had a question that maybe is related to that one. Do you care about the properties of the photons, like their wavelengths, or do you necessarily encode the quantum information in polarization states, or again, is it just a generic quantum state of the photon that you're considering?
In terms of communication?
Well, for any of your applications, does it matter what the wavelength of the photons are, or is that a detail that you don't really care about?
As I say, I'm not an expert on that, so I cannot elaborate on that. I cannot really answer that question. But yeah, what I to care in this communication, it's about the coherence of the qubit, that whenever a state is sent, let's say from one processor to the other, the state is still there, right? That is
Right.
it's not lost in this communication link.
Yep. Okay. It looks like the person who was asking the question has pivoted to a slightly different question.
Okay. Which mode of computation is better, superconducting circuit and ion trap technology? Okay. So you mean that what mode of computation is better? Okay. So they will have like advantages and disadvantages. So right now, I mean, like ion trap and superconducting, they are, let's say, in the forefront of this race, because they have several, like the good thing, for example, about ion traps that we have nowadays, at least, is that you have like all-to-all connections, right? And therefore you don't have this problem of mapping and moving things around. And superconducting qubits, on the other hand, you have this limitation, but still I think coherence time, or I don't remember, I will have to look at the slide, they have like a slightly better coherence time or error rates. I don't remember by heart, but yeah. They are kind of comparable, and in both technologies, we are using the same model of computation. So we are using circuit-based model of computation, in which your quantum algorithm is described in terms of gates and circuits. The circuit nothing does not share the classical computer. Is that okay? Yeah. So about the mapping problem, this is not exactly in classical computers, but for example, whenever you use, like, say, like in distributed, let's say in classical computers, of course, you have this thing about where allocate several tasks, especially when you go to distributed system and you want to parallelize things. In FPGAs, you also have this problem of allocation, in which you allocate different, let's say, parts of your algorithm or your application. But it's not exactly the same, because here we will need to know, let's say, the nitty-gritty details or the specific constraints of each device. So I think I will go like one let's say, a step further. And it's also hard problem for classical compilation. What there are similarities in classical compilation is, for instance, in terms of scheduling of operations. In that case, there are a lot of similarities, with some differences that, for example, in quantum computing, you have this commutativity property that you don't have in classical computers, and also the other difference, and in fact, is this in memory computing model of computations, in which you have to assign, let's say, operations to each of the qubits. So there are indeed some similarities, but there are like a lot of, and so there are some principles that can be reused, that, for example, in terms of scheduling, but due to the property, let's say, of quantum mechanics, there are also like a lot of difference that you have to really think of and come up with different strategies. From a stack perspective, how important is the ability to have interaction between remote qubits? I will say that have interaction between remote qubits, you mean like, yeah, you can interact with any pair of qubits. I think that, as I say, when I explain the mapping problem, that is one of the main issues in the current technologies, that we don't have all-to-all interactions, because that means that we have to add extra operations now. That is a problem indeed for current devices, especially because we don't have any kind of protection or quantum error protection. So therefore, that really affects or impacts the fidelity of your algorithm. Once we go, let's say, to universal quantum computation, in which in principle we use quantum error correction or any other methodology that we can come up in the next year, and your computer will be protected, maybe it's a bit less important. Yeah. But still, so ideally we would like to any qubit, ideally we would like any qubit to interact with any other qubit without having to move them. Okay. What are the fundamental differences between quantum assembly and classical assembly languages? So quantum assembly languages indeed are inspired by classical assembly languages. So right now, the quantum assembly languages, I will not say that they're like the classical in the sense that it's just a description, as I show, especially when you use the gate model or circuit model computation. It's just, let's say, a description of your circuit. So some of the assembly instructions or quantum assembly instructions that we have, as you show, as shown in the previous slide, and in the Quasar, for example, the C Quasar that we use in our lab, but also in Open Quasar that is used by IBM, is just a Hadamard with Q1 or a signal Q1, Q2. So it's just, in this case, just a description of the circuit. So yeah, so there are like many differences in the sense. So some let's say classical instructions can be also used, and they are necessary, and they are based on the quantum assembly, like classical quantum assembly. But yeah, there are other instructions that are not in classical, of course, and they have to be redefined in the quantum, let's say, world.
Okay, Carmen, thank you again for giving an excellent talk and agreeing to speak with us today. We'll go ahead and move on to the poster talk, which is going to be given by Shiru Yan at University of British Columbia. And let me end this recording.